Cedric, thank you for agreeing again, and please go ahead.
Yeah, thank you. Hello, everyone. My name is Cedric Kilian. I'm from INRIA, University of Rennes in France, and I will share the regular session entitled NOCS and Emerging Applications. So we will have 2 long presentations. Each presentation is 15 minutes of talk, and we will have 5 minutes of question and answer after that. So let's start the first presentation. The first paper is untitled RB-OLITs, worst case reorder buffer size reduction method for 3D NOC. The speaker is Jianming Li. Jianming Li received his PhD degree in electrical and electronic engineering from the University of Auckland in 2016. He is currently a lecturer in Hefei University of Technology. His research interests include hardware accelerator design for machine learning applications, network-on-chip analysis, timing analysis, and design space exploration for time predictable systems. So, Jianming Li, you're free to start. Yeah, can you share your screen? And turn on your microphone, please.
Hello, can you hear me?
Yeah, we can hear you.
Okay, I'm gonna share my screen. Okay, I have shared my screen.
Okay, we can see your screen if you can switch to presentation mode. Okay, perfect. Thank you.
Okay. Can I start now, or?
Yeah, you can start. Please go on.
Okay. Hello, everyone. Today I'm going to present our work named RB-OLITs, a worst-case reorder buffer size reduction approach for 3D and NOC. My name is Jianming Li, and I'm from Hefei University of Technology. And first, our research, the background is 3D NOC is an emerging technology which is a promising successor to the traditional bus interconnection architecture. And the packet-based 3D NOC paradigm is highly scalable and fundamentally decouples communication from computation. And it has advantages of low communication delay, low power consumption, and it has high data throughput. But however, it has some drawbacks, and its complexity. It forbids us from further exploit this potential of this technology. One of them is in-order packet delivery. It is a crucial question for a majority of applications. For instance, multimedia or cache coherence protocols. The problem is that data packets arriving at the destination may cause the out-of-order problem. So calculation and reduction of worst-case reorder buffer size has become a pivotal research topic. The calculation and reduction of the worst-case reorder buffer size also corresponds to the 2 contributions of this paper. First, we address the problem of how to calculate the worst-case reorder buffer size. And the second, we develop a splitting configuration approach to reduce the worst-case reorder buffer size. So let's take this picture as a motivating example. Here, we depict the 3D NOC architecture with 3D mesh topology. Each circle in the 3D mesh architecture denotes a router that is capable of performing multi-path minimal routing function. So each router is connecting to a local component, typically a processing element, through network interface. The reorder module is located within the network interface, which is responsible for reordering the packets in an orderly manner before forwarding them to the local PE. Therefore, the PEs are ignorant about the reordering procedure, so that the modularity and scalability of 3D NOC architecture can be maintained. In this example, we have 3 subflows, which are F1, F2, and F3. They are splitting in 3 different paths, and because of different path delays, the arrival of their data packets may be not in the correct sequence. Therefore, we need this reordering module to put them back to the correct sequence. So in this case, we have the reorder buffer size of 6 data packets. So now let's take a look at this motivating example and go further. We want to develop a method to calculate the worst case reorder buffer size. So we take a look at the scenario where only 3 subflows exist. So now, corresponding to the figure in the left side, we have the subflow ID analysis here. We assume that the order of sending data packets is F1, F2, and F3. We further assume the delay of F1 is the highest, the delay of F2 is the second, and the delay of F3 is the lowest. Therefore, the worst case happens when F3 reaches the destination node first, F2 the next, and F1 the last. So based on this assumption, we can calculate the worst case reorder buffer size using the equation in the right-hand side. And because we only take an example of 3 subflows, we need to generalize into n subflows, any number of subflows. So we extend the equation and further derive the SRB max, which is the worst case reorder buffer size for any number of subflows. Note here, the D max bar means the maximum of all DI bar. And here the delta Tn represent the packet injection intervals. Okay, now let's take a look at the calculation of the worst case reorder buffer size based on network calculus theory. So it is the theory to analyze the worst case scenario, and the result must be in a safe side. So there's must not be exceeded. So this picture in the top represents the idea of abstracting the system into abstracting the design into systems, and it is used to apply this network calculus theory. So the steps to derive the worst case reorder buffer size is there are 3 steps. The first one is traffic splitting. The second one is equivalent service curve and delay bound calculation. And the third step is calculation of the worst case reorder buffer size. Let's skip all the tedious derivation of the equations and give the final results, which is also equation 5 in the paper. So this is a big equation, but it represents the method of calculating the worst case reorder buffer size. Based on the discovery and insights of examining this equation, we further develop a method to reduce the worst case buffer size. The method is we use 3 steps to calculate a clever way of splitting the data traffic. So it will result in smaller worst case buffer size. So the first step is to calculate the adjacency matrix in order to capture the local traffic splitting state. The second step is to calculate contention matrix. The contention matrix is used to capture the global network congestion information. So the final equation for calculating the contention matrix is given in the right-hand side. Note here, the Ri and Bi are flow rate and burstiness of subflow I, respectively. And the epsilon and beta here are the impact factor of Ri and Bi, respectively. The third step, we can derive a congestion factor. Based on the contention matrix, we use congestion factor to predicate the congestion state of a subflow. Therefore, the congestion factor of subflow Fi, which can be called lambda Fi, is defined as the total contention of Fi. So based on the observation when we previously derived the equation to calculate the worst case reorder buffer size, we find that both the items Ri and Ti contain the factor rho, which is the splitting proportion of the subflow, indicating that the worst case reorder buffer size may be affected by the square of the conjection factor. Based on this observation, we further extend the previously developed OLITS method, OLITS, which is also developed by our team. We further extend it to use a novel conjection factor. So we get the equation 20 on the paper. And here RS is the splitting proportion of subflow FSD. So this new splitting configuration can be captured using the Ohm's law-like calculation. And here the PSD is the final splitting configuration derived for subflow FSD. So we expect that this new splitting configuration can result in smaller worst-case reorder buffer size. So we do the experimental experiments and get the results. Firstly, we verify the splitting proportion from 0.1 to 0.9 along the x-axis, and it is a synthetic pattern. And the y and z directions get half of the rest. We have obtained a maximum optimization of 53.2% compared with uniform split, which is a very basic splitting configuration. And also we compare with the OLITS method, which is a work presented also on NOCS, which is also developed by our team. So compared with OLITS, we get maximum of 20.88% improvement. And on average, we get 19.09% of improvements. So this improvements indicates that using the new configuration, the splitting configuration, we can indeed reduce the worst case reorder buffer size by average 19.09% comparing to OLITS method. And then we also compare another scenario which we reduce the contention flows to 2 contention flows, and then we get another set of results. Comparing with OLITS method, we get the average of 9.28% of improvements. While reducing the worst case reorder buffer size, we worry that it might increase the worst case delay bound, which is not a good thing. We want to at least maintain the worst case delay bound. So we did the calculation of worst case delay bound. The result shows that our method will not deteriorate the worst case delay bound, and it stays at the same level of OLITS method, even with a little improvements. And then we also study the impact of injection rate with varying burstiness. And it shows that with the increasing injection rate or burstiness, the worst case reorder buffer size increases accordingly, but at a steady pace. Finally, we apply our method on the industrial pattern. This is called DVOPD, which is an example, which is based on actual design constraints and performance trade-offs. We map the DVOPD application onto 3D NOC architecture. The application graph and the mapping scheme are shown here. And we have 43 contention flows in this scenario. And the result shows that we achieved 12.8% maximum improvement on worst case reorder buffer size using RB OLITS method. And on average, the improvement is 6.76%. While the worst case delay bound remain almost unchanged compared with OLITS method. There is only 0.06% of difference. So in conclusion, The contribution of this work has two folds. The first, we present an analytical model for calculating the worst case reorder buffer size. So we can support arbitrarily number of subflows. The second contribution is that we present a novel traffic splitting configuration methods, which called RB-OLIS, for reducing the worst case reorder buffer size, also in the analytical model. So it has an improvement of 5.9% to 20.9% in most cases, and it can save valuable buffer size resources on chip because the buffer size is very costly in terms of hardware resource usage. So that's all. Thank you for listening.
Thank you, Jamili.
Thank you.
I also forget to say that your work is a candidate for the Best Paper Award that will be selected and announced at the end of the day. So thank you again for the presentation. Now it's time for question. So we have a few minutes for that. So you can either raise your hand and we will give you a way to talk, or you can directly write in the Q&A panel.
We can wait for some questions to rise.
Yeah, I'm looking for some rise hand. So I have some question while people can still ask question and write things. So with your techniques, is there a heterogeneity in terms of buffer size within the architectures?
Sorry, the internet connection is poor. Could you please repeat your question?
Yeah, of course. So do you hear me clear now? Is it better?
Yes, better now.
So for the reorder buffer in each call, do you have with your methods heterogeneity in terms of reorder buffer size among the architectures, or all the reorder buffer have the same size in all the destinations?
Okay, very good question. Depends on the applications mapped onto this NOC. I assume that all the reorder buffers have the same size because it is not dedicated to one application or several applications. But there's a hot topic called domain-specific architecture. In that case, I think it can be different. At least we can divide some regions on the NOC, where one region has smaller reorder buffer size and later another region has the bigger ones.
Okay, thank you for your answer. In terms of evaluation, are you looking for the worst case? What happens if finally you underestimate the size of the reorder buffer? What will happen then?
Okay. Because it is the power of network calculus, this mathematical tool that can guarantee that there will not be a violation of the worst case. And it has been proven by previous several papers. We follow the same theory to calculate the worst case reorder buffer size. And it is honestly a pessimistic estimation. And the reality should be smaller, much smaller than the calculated value. But in order to achieve the safety, we have to follow the theory and network calculus theory and get that value. So even though we haven't tested in this paper, but we have done the evaluation simulation previously in our previous work, that our calculated worst case values are very safe.
Okay, thank you very much, Jamili.
You're welcome.
So,
you're welcome.
If there are no more questions, maybe we can go for the second presentation. So thanks again, Jamili, for your presentation.
Thank you. You're welcome.
So I think we can directly start because we had some delay. So the second, so Abhijit, maybe you can switch to main title, main presentation. Okay, so the second presentation is entitled Many ported and shared memory architecture for high performance ADAS SoCs. We will have two speakers for this presentation. The first speaker is Hao Luen. So Hao Luen is the chief SoC architect of Horizon Robotics. His current interests include domain-specific SoC architectures for ADAS applications, multi-die SoC architecture, and data flow-based scheduling. He is an IEEE senior member. The second presenter will be Yu Yao. Yu Yao earned his master's degree from UCLA. He is currently working at Horizon Robotics as an ASIC design engineer, focusing on memory hierarchy, system scheduling, and data path optimization. So you can start now.
Thank you. Can you hear me okay?
Yeah, we can hear you. And I think we can see your screen. Perfect.
Thank you for the introductions. And today, my colleague and I will be presenting our paper, and we are very honored to show our results and prototype findings here. Here's the agenda for today's talk. I will cover the relevant background, and I will make an introduction to the architecture. And you will take over to share our results, and he will finish our conclusions at the end. This is the relevant backgrounds as shown in this picture is a typical ADAS and HAV processing pipeline. Starting from the left, the data, the raw data will be fed in by numbers of cameras, lidars, and radars. And this will be the basic constructing elements for the object identification and the tracking phase. This massive data will be further processed by many heterogeneous machine learning accelerators, CPU, DSP, and so on, so that we can detect the tracked objects, we can do the predictions, and at the end of this phase, we will fit in the data to Fusion, where 3D coordinate space will be construct, and the vehicle locations and tracked objects will be put together for planning phase. So the planning phase basically will start to calculate the motion trajectory and also correlates with the mission informations. And then it will make a very concise and reliable decisions at the very end. Along this pipeline, there are a few key characteristics, starting from the data collection all the way to track and fusion planning. Basically is ASLB level kind of compliance or maybe lower. However, at the very end, when we reach the control decision, we need to have ASLD as David kind of compliance so that we will have the highest level of safety to make sure there's no surprise happen at the end. And in order to sustain a huge processing power to provide correct real-time decision, on-chip shared memory architecture is really needed to improve the overall performance and also lower down the power consumption and shorten the end-to-end processing time. And on this page, we list out the system needs for such a on-chip shared memory architecture. However, I really wanted to summarize and give the highlights on the architectural challenge. First and foremost is such a high volume shared memory architecture really have a very memory dominant layout. And we will have a sea of the memories to build up the layout. And the first thing we'll present is very non-uniform memory access. And because it's a parallel access shared memory architecture, there will be a lot of memory access contentions that we need to address when we share the memory contents. And because of the ADAS and HAV application, we really need to have isolations if necessary for some particular type of applications. So sharing and isolation are really a double-edged sword. You know, we really need to strike a balance to get a satisfactory result. Of course, for any engineering practice, we need to have a very scalable architecture. One for the physical implementation perspective, and secondly is for the, you know, we can easily migrate the same architecture from one product to the next, and from one technology node to another. And last but not least, we also need to address that we really need to heavily optimize and customize for the EDAS and HAV payloads. And the nature for this kind of payload is we have you know, tens of hundreds of kilobytes of data, a big buffer we need to process. You know, the image data and you know, the region of interest image of data normally come out a pretty big size. So for such a kind of a characteristics of access, we really need to heavily optimize for big buffer access. We need to provide very consistent access latency, while we need to provide high throughput at the same time. This is the architecture, logic architecture. You can it represents, and it also represents our physical implementation layout. This is very domain specific because we really optimize this architecture for the EDAS application. This is a very hierarchical one because you can see that we have an even number, and here we have 4 clusters. Because of the even numbers, we will evenly split out the traffic nicely for, you know, the common burst transaction. For example, burst 4, 8, or 16, which is very common for AXI or other common bus protocols. And the masters of the traffics, we can, you know, channel them in for all different directions. And this is a really combine the logical and physical diagram. So all the traffic is coming from 4 different edges, or, you know, we can also put in coming from 2 different edges, as we shown later on in our physical implementation results. And we heavily rely on this splitting and dispatching structure. And this is a multi-level dispatching structure, which is we really employ it for one to average out the NUMA traffic. Second, we also need to reduce or mediate the memory access contentions at the same time. And to repeat what I said in the previous page, we need a very hierarchical structure, because this will help us to tackle such a very heavy memory, a very big volume memory architecture for the engineering practice purpose. The hierarchical level of architecture will really smooth out our timing closure and the physical design experience. This is a zoom-in look of how the randomization and how the NUMA effect be mediated and averaged out. For example, you have, you know, I just said that we have a common burst 4, 8, or 16 traffic burst transactions, and here we have 4 different clusters. And here, like we normally split it out across multiple clusters, so that for burst 4 transaction, every cluster will have 1 bit of data that fall into the each cluster. And if you have a burst 8 or 16, you ended up we have 2 bits or 4 bits fall into each cluster. By doing that, one is we can easily average out the access latency for big buffer transfers. And secondly is every time you can see that even though you have 4 bits fall into the same cluster, but it will end up with 4 different bank groups, which is heavily mediate the access contention at the same time. Here is the SRAM array organization. The memory arrays we organize in a 2D kind of layout as I shown in this picture. So within each logic bank, we have multiple sub-banks. You can see that it's going to the vertical direction. And by employing a very typical interleaving schemes, a linear address can be spread across, horizontally across different logic bank. And the way why we're doing so is because first, we can keep spreading and splitting a traffic from any master all the way from start to the end of the data path to the memory bank. And secondly is, if we have two different masters that access to different sub-banks, different slice, if the horizontal as I drawn here is a different slice, we naturally provide isolations between the two different processing elements. And on top of that, we also putting in extra duplicated logic at arbitration at each bank so that we can be ASLB as boy kind of compliance. And to achieve a higher ASLD or C kind of levels compliance, we have to leverage software and algorithms so that the same result can be compared against each other before we reach a conclusion. That's kind of a common practice in this industry. So a higher levels ASLD protection can be easily achieved. So that's all I have for the architecture introduction and the background introduction. I will pass to my colleague to take over from here to share the results. You please take over from here.
Okay, thank you, Hao. Hello, everyone. Hao, can you help me share the slides?
Oh, okay. I can share back. No problem. Okay, let me move to the next page.
Okay, thank you. So here is the setup and parameter for the prototype that we present in this paper. So it holds 32 megabytes functional memory storage, and it's consisted of half K SRAM macros. And it can host 16 accessing masters with 256-bit read and write data bus. And the AXI5 read data trunking feature is supported. And also, so as shown in the previous slides, two levels of splitting and distributing NOC logic is implemented, and one final level of arbitration is implemented before the SRAM banks to merge all the traffic from masters to every single SRAM macro. And as mentioned before, ISO 26262 ASOB function safety is implemented, and to achieve that, data path end-to-end ECC and SRAM ECC. So besides the 32 megabytes of function storage, we also have some storage for the ECC bits. And also master-to-master isolation is implemented. So at the implementation stage, we sign off the NOC logic at 1 gigahertz and the SRAM macros at 500 megahertz. So this difference between the SRAM macros and the NOC macro is for several reasons. One is that at our technology node is we try to find one SRAM macro that achieves great balance between power and latency, and also the flexibility of the routing near the SRAM macros is very important for us to achieve better SRAM density because of the half K number. That's a lot of SRAM macros inside the chip. So in the end, we choose 500. We choose SRAM macro that achieves a pretty good balance between the power and the area, and that's why we are doing this at 500 megahertz. And the outstanding capability for each of the master is we can hold 8 commands at entrance, and we have a buffer worth of storing 64 splitting and dispatching bits for each direction of each port. So each master has two directions, read and write, and the storage and for the bits and the command is for each master and each direction. So to sum up, we have the prototype supports 60 masters, and it has 4 clusters as shown in the previous example, and 4 SRAM groups inside each cluster. So it's a 4x4 topology. Okay, thank you. So to verify the assumptions we have for the architecture, we first built a simulation to test the design. So on the left side is a result of we are having multiple parallel masters accessing the SRAM banks. So we increased the accessing master from 1 to 16 altogether, and each master is injecting randomized address access to the design, like at full throughput, at full capacity. So it's keep injecting new bursts into the design. And we can see that, okay, on the top of the diagram is the throughput number. We can see the throughput number is really, really high, it's stable, and it's stabilized even though the accessing master varies from 1 to 16. So it's almost 100% for both read and write. And for latency, so we do see the transaction latency. Also, the latency here is measured by each transaction. So it starts from once a transaction leaves a master and the last response to the time when the last response comes back. So we do see the transaction latency
There's 2 minutes remaining.
Okay. So, the transaction latency number increased with the number of accessing masters, but actually the data throughput is pretty stable. So we built a second test to test the bulk data transaction. So we can see after the initial pipe latency, we can achieve almost 100% throughput. So the bulk data latency is very consistent. So next page, please. So then we build to better mimic the traffic in ADAS simulation. We kind of we built another test that for half of the masters running with CNN network traffic extracted from our in-house algorithm, and the other 8 masters running with YUV frame data with the ROI region cropped. So the ROI data is more its continuity is better. It's better than the CNN network, but we can see like in the results, the latency for the image master is better than the machine learning master for the latency, but the throughput is the same, still almost 100%. Next page, please. So for the same test, for the read results, the read latency is smaller than the read latency, and is almost the same for no matter what kind of payload is used. And also the throughput is stable at almost 100%. So this real traffic traces shows that our design is very stable to most kind of payload, especially for the throughput number. So okay, so the prototype went through the entire physical design. So we did timings of at 1 GHz for the NOC and the 500 for the SRAM at 7 nanometer, and we didn't use any ULVT cell, and 10% limit for LVT cell is used, and this leads to a smooth timing closure. And the final area is less than 30 square millimeters, and the utilization rate of the logic is around 40%. It's kind of wire dominant design, and the hierarchical design enables very smooth.
Thank you for concluding.
Okay.
You can just conclude, please.
Okay.
I'm sorry.
Okay. So So we kind of achieve a close to 100% throughput for the ADAS payloads, and enables high performance design while achieves low power consumption and acceptable area. And it proves a modular and scalable architecture is friendly for physical design and implementations. And moving forward, we actively investigate to further shorten the latency number and achieve better area density and support more master ports. Applied architecture to work with 3D integration and chiplet techniques. I think this concludes our presentation. Thank you. Thank you for the opportunity.
Thank you for the presentation. We have time for one quick question. So you can raise your hand or write in either the chat or the Q&R panel. So I have one question. With your architectures, finally, if we look for larger architectures in terms of scalability, I think that so you have finally more input to the SRAM. So in terms of arbitration, so we will have more latency. Is it easily scalable, or have you tried to look at that?
Maybe I gave a first cut. You can add on if I miss anything. Yes, I think this is a very scalable architecture. Even though we've shown our results like a 32 megabyte, and we have demonstrated it can be easily scaled up and out to a higher memory capacity, because of the way that we organize the memory in such a manner. We can see a slightly higher average latencies if we have a bigger shared memory content.
Okay, thank you. Thank you so much. Thanks again for the presentation. So this will close this session. There is a break for 4 minutes. So thanks again.